Welcome to our project Path Planning with D Lite algorithm and computer vision under the course of Artificial Intelligence for Robotics. So let's delve deep into this. So these are the table of contents that we will be seeing in upcoming slides. So we have come up with planning of a path using D Lite and computer vision for a differential drive robot. So basically our solution includes capturing image from camera and selecting start and goal, then finding path using D Lite and send the corresponding commands to robot and it will execute until it reaches the goal. So our core objective includes that robot should follow an optimal path and there should be a proper path from start to end. Robot should detect obstacle and avoid it. It should replan path if necessary in case of obstacles are dynamic. The technical targets includes that error should be minimal. So these are the assumptions that we are taking into considerations, like there should be sufficient light in the environment, obstacles should have a dark color and no shadow of them, the background should be plain, sufficient space should be there, and our robot moves in only 4 cardinal directions. Here are the PAs of our robot. Performance includes accuracy and reaching the goal. Environments includes level surface, sufficient light, dark obstacles. The actuators are motors, wheels, ESP32, R-pipe, and the sensors are pi camera, gyroscope, and coders. So here's the workflow of our whole project. Camera captures feed, converts it into the grid using OpenCV, and identifies robot using AprilTag. On selecting goal, D-Star Light generate paths. Command is given to the ESP32. The robot drivers execute the command and robot position is located in the next frame if it has been updated or not, and then corresponding commands are given again until the goal is reached. So here's how the image to grid conversion happens. For this, we convert the frame that is captured through camera into grayscale, then divide into rectangular patches of cell size. Considering our robot size, we have taken it into 120 cross 120 cross pixels because the camera would be mounted on a ceiling. So height should also play a major role. That's why we have chosen this pixel size. Then for each cell, it checks the brightness, or we can say the intensity of that pixels contain into that grid. And if they are greater than threshold, then it marks them as obstacle. Otherwise, keep it free cells. So these are the hardware and software that we have used for our project. Here's the chassis, ESP32, two wheels encoder for odometry, gyroscope for direction, and a voltage controller for limited voltage supply to our ESP32. Then the modules we have used are OpenCV, NumPy, AprilTag for robot detection, and Wi-Fi.h for sending commands from RPi to ESP32. So here is our final robot. You can see there is a voltage regulator, wheels, encoders are also there for odometry, ESP32 for controlling the motor drivers. So now I'll be talking about methodology. Before that, I would like to explain about the April tag. So April tags are visual markers. Basically, they are like QR codes. Has unique ID, has precise X, Y, and yaw. So they can be used for position and orientation detection. Here comes the D-star light algorithm. So it is an incremental search method that plans a route. But if there is some obstacle arrives or the path or the weight changes, it updates from there only. Unlike a start that will reroute from the starting to goal. But D-star light on the fly updates its path cost and reroute from there only, saving a lot of time and effort. So the algorithm is simple. Just initialize all the nodes and as unexpanded, apply best first search until the system is consistent, moves to next best, and if any edge cost changes, then track the heuristic change and updates the source node of changed edges. And again, back to step 2, like best first search, until the system is consistent. So here's a small explanation how our frames converted into this grid form. So as the video stream captures the ground, at every second a frame is chosen and obstacles are mapped. So for robot detection, we are using AprilTag, and for better path planning, we are also choosing the start and goal. So D star light will choose the next node until the current node is the goal node. Then send the command to ESP32, which will concurrently send this command to differential motor drivers to execute the command. After executing the command, robot position is updated. Hence, our camera also captures the next frame, or in the next frame robot's new position, and updates the path and send the new command. So here we can see that the green dots are representing the path, and the selected boxes are showing the start and goal, and the red bar shows the obstacles. So here's the algorithm for the movement of robot in ESP32, how it works. So it initializes the hardware, like setup or configure the file, update the sensors, data, and like from gyroscope. And if it receives the UTP command that we have sent from RPI to ESP32, it passes the command, like if the command is forward, so it moves forward some ticks, and if it's like turn, so there would be a command from RPI like left, so it will turn left 90 degree. Since we have considered only four cardinal directions, so we are not mentioning in command the degrees, because it's already understood that the turn would be of 90 degree only. And also we have used PID controllers to achieve the required target. If the robot drifts from its way, the PID controller algorithm tries to keep it into track so that it does not drift away. Here's both the software and hardware are of different thing, and we are integrating. So the integration happens is required because we are sending command from RPI to ESP32, which is a hardware level device. So for that, there should be a integration method. So we are using UDP protocol for sending the commands over from RPI to ESP32, subject to the condition that both are connected to the same Wi-Fi. So the key challenges that we faced during the development of this project was the managing lightning conditions and colors of the floor, robot, and the obstacles. Even the robot body detection was a bit challenging, and error minimization is always a part of challenge in any project. So here's the working video. So on left side, we can see that the robot moves. The command are given through RPI at every frame is being updated. And on the right side, we can see a screencast of a kind of simulation, but real, because it's a live feed from the camera. So the robot moves until the goal is reached. And here's are the contribution made by the team members. And the module that we have used from our course includes robot anatomy and kinematics, mobile robot sensing and perception, and obviously robotic vision. So our future work includes implementing reinforcement learning instead of AprilTag, making robot move in many directions. So here's the reference that we have taken from different research papers. And for error solving, we have used LLM like ChatGPT. Thank you. And special thanks to our professor, Dr. Chandraprakash sir, and Dr. Saurabjit Behra sir for their wonderful guidance and help. Thank you.